That's what somebody did last class. They were like, "Can you help me with this? I'm about to break my Chromebook." So don't get that frustrated. Just take it easy. We'll get through it. Just to recap very quickly, yesterday we talked about protons and neutrons. The atomic number is just the number of protons. When we talk about the mass number, let me just emphasize that. The atomic number is going to be on top of the box on the periodic table. When we talk about mass number is the protons and the neutrons. And the reason we need to talk about mass number is because there are things called isotopes. So basically, not every element, but most elements have something called an isotope. They all have the same number of protons. So like, for instance, if I have carbon has 6 protons. Most carbon has 6 neutrons also, so its mass number is 12. But there's a certain type of carbon called carbon-14 that has 8 neutrons, so its mass number is 14. So anytime they put the number right after the element, they're giving you the mass number, the protons and the neutrons. Just to give you an example, carbon-14 is radioactive. You all have it inside of you right now. We eat it, we drink it, we breathe it, it's in everything. And when you hear about the term carbon dating, when we date, we find out how old things are, like old trees, old human settlements, different stuff like that, old weapons. Carbon dating is used for that because as long as something is alive, it's eating and ingesting carbon-14, and you have a certain level. Like everybody has a baseline level of carbon-14. The day you die, you stop ingesting carbon-14, and it's slightly radioactive. And so over time, that carbon-14 will decay into a different element, either carbon-12 or something different. I forget the exact chain from it. It might actually be nitrogen. But it decays away from carbon-14. So if we find an old body or an old piece of wood or something like that, we can go in, measure how much carbon-14 is in there, and know how long ago specifically it died, which is very useful for dating old human settlements, different indigenous peoples' areas. There's all sorts of things you can do with it. And so radioactive elements and isotopes are actually very important for chemistry type work. So if it has a different number of neutrons, it is called an isotope. Remember that the mass number is the protons plus the neutrons. So if you add them together, you get the mass number. Here, helium, if you look at helium on your periodic table, it has 2 protons. Most helium has 2 neutrons. So helium-4 is how we describe that because the mass number is 4. 2 protons, 2 neutrons. Carbon has 6 protons. It also has 6 neutrons most of the time. So it's carbon-12. Carbon-14 would be the radioactive one. And think of it this way. Protons are all positive, right? Can I put a bunch of positive magnets right next to each other? No, they're going to repel. They're going to want to push away from each other. So the neutrons are almost like packing peanuts. In order for me to put all these positive protons in the same box, they're going to want to get out of there. If I put things in between them that aren't positive and aren't negative, it's going to help me pack all that stuff really tightly close together. And so the neutrons allow everything to sit in the nucleus and be nice and stable. For your lower elements, your smaller elements, it's about 1-to-1. Helium has 2 protons. It also has 2 neutrons. Carbon has 6 protons. It also has 6 neutrons. The bigger your atoms get and the more protons you get, the more neutrons you will need to kind of balance that out. So the bottom one here, copper, if you look up copper, it is Cu. It has 29 protons. The atomic number is 29. But this says copper 63. So it actually has 34 neutrons. 29 protons, 34 neutrons. So to keep those 29 protons in place, they need more than 29 neutrons. They need 34 neutrons to kind of keep everything stable. So just know that the smaller it is, you kind of have 1-to-1. The bigger it is, you will need more neutrons usually to make sure that it's stable. Isotopic notation, you'll have a couple questions where you actually have to go into Sapling and move your cursor around and delete some question marks here and put numbers where the Z and the A are. The top number is both protons and neutrons. That's your mass number. The bottom number is your atomic number, just your protons. And I actually have that written on the board. So if you get to that problem and you're like, I don't remember what to do, look up here. The top number is protons and neutrons. The bottom number is just your protons. And to be honest, in sapling, you'll want to like click on it to get to that point. It's not going to let you. You have to use your arrows on your keyboard to navigate in front of these and then delete them so you can put a number in there. Let's see. So here's an example. They want to know how many neutrons does this atom contain. The bottom number is just protons. It's your atomic number is 8. The top number is protons plus neutrons. So what do you have to do? You just subtract. You're going to take the 17 minus 8, which leaves you how many left over? 9. 9 neutrons. So 17 minus 8 is equal to 9. That's your neutrons. I have 8 protons, 9 neutrons. If I add them together, my mass number, which goes on top, is 17. So just simple math. You just got to know where the numbers go. Value given for elements mass on a periodic table. Now, you'll notice that on the periodic table, the bottom number in each square usually has a pretty big decimal. Carbon, it's 12.011, not exactly 12. For oxygen, it's 15.999. The reason for this is these numbers are the average atomic mass. So if that element has isotopes, we're going to average all of them over the entire planet and figure out what that average atomic mass is. For instance, chlorine, there's a chlorine 35 and a chlorine 37. This 75.77% is chlorine 35. So the brown part of the pie chart is chlorine 35. The blue part is chlorine 37. Find chlorine on the periodic table. What's the mass at the bottom there?
35.45.
35.45. So it's not 35 and it's not 37 and it's not right in between. You're not just averaging them like they're equal because they're not equal. You have a lot more 35 than you do 37. So it's not going to be 36. It's going to be closer to 35, but higher than it because the X number is 37. It's higher. So when you average these out, you will get that decimal. And that's actually what you're going to have to do for some problems today. Know that some of them don't have any isotopes. Some of them only have one isotope. Chlorine 35 would be the stable version. Chlorine 37 would be the unstable radioactive one. For others, you have a lot. Chromium has 4 isotopes. Germanium has 5. And SN, someone find SN and tell me what element that is. It's in the blue, the light blue.
10.
It's tin, the metal tin, like a tin can. Although our tin cans now are made of aluminum, not tin. But yeah, tin, the metal. It has 10 different isotopes, and they're all kind of spread out. Some of them you have more of, some of them you have less of. But this kind of shows you that they're not all equal. And so when you average it and get your percent abundance for your average atomic mass, there's a little bit of math you have to do here. So doesn't that look fun? Math class stuff. Yeah, you're going to like this. 3 steps. These are actually pretty easy. It's not too bad. Step 1, change the given percent to a decimal. How do you change a percent to a decimal? You move the decimal to the left twice. So if I have 50%, what's the decimal for that?
0.5.
0.50. Yeah, 50% is 0.50. 75% is 0.75. So you just move the decimal twice to make it a decimal number instead of a percent number. So step 1, take all your percentages, move the decimal twice to the left to make it into a decimal. Step 2, you want to multiply the mass that they give you, not the one from the periodic table, but the one they give you for each of those percents that you turn into a decimal. So you're going to take the percent, turn it into a decimal, multiply it by the mass. Step 3, you're probably going to have more than one. You're going to have to add these together. And I'll actually leave this on the board for y'all so you can see the steps. And I'm going to do a couple examples real quick. So here's your first example. We have 2 different isotopes of silver. We have silver 107 and silver 109. If they don't give you an actual decimal mass, you can use the mass number here. Notice they're pretty close. 107 is 106.91. 109 is 108.9. If they didn't give you these, you could use these numbers and you'd be just fine. But if they do give them to you, let's use them. So step one, I need to take my percentages and turn them into a decimal. I'm actually going to turn the lights on real quick. I've done this over here. Instead of 51.839, I moved my decimal twice and I have 0.51839. And instead of 48.161%, I moved my decimal twice and have 0.48161. Now I'm going to multiply by the mass that they gave me. For silver 107, the mass is 106.91. For silver 109, the mass is 108.90. So I take my percent, which I've turned into a decimal, multiply it by the mass, and I get an answer. And I'm actually going to get two answers. Now, the last step is to add them together. But think about this. Are these pretty close in percentages? Yeah, it's almost 50-50. It's a little bit off, but it's almost 50-50. So if I have 107 and 109 and I take an average and it's 50-50, it should be right around 108, right? That's going to be pretty close to what we have. So when I do this and I add these last two numbers together, I get my answers, which is 55.42. It was actually 421, and I didn't write the one down. Here. Come on. 421. And then, my bad. 52.447. When I put these in the calculator, I'm not going to bother to do it now. I did it last period. And then you add these together, and you get 107.868, which is pretty close to 108, right? And so that's a pretty good average there. So if I average all the silver over the entire planet, it could weigh, all the silver is going to weigh 107.868. And if you look and find silver on the periodic table, maybe it'll work this way. Silver's Ag, yes, 107.868. They have a 2 at the end, but I got it right. And so that's how they got to that. Now, there is no silver that weighs 107.868. It either weighs 106.9 or 108.9. But if you average all those together based on how often they're likely to come up, you get that 107.868. So that's what they're doing here. And you will actually have a problem on the assignment where you have to do a lot of this. There's 5 numbers they give you. You move all the decimals. You multiply them by the weights. You get your 5 answers. And then last step, you need to add your answers together. So if you have scratch paper, make sure you're using it, because if you try to do all this in the calculator, it might get a little bit cumbersome. So let's see. Do they have anything else? I already went through all this. Ions is for tomorrow. So go ahead and get started on it. People at home, if you have any questions, I've already received a couple emails from students and emailed back. So please send me an email, and I will be able to help you out through that format. And yeah, depending on how fast everybody gets this done, we may or may not work on this tomorrow. So keep an eye out on Google Classroom tomorrow to find out what the assignment is. Or if there is no assignment, you'll have to fill out an attendance form. Thanks. Have a nice day.